Hi there, and welcome to our final TTED 4060 lecture of this strange COVID day fall semester. And anyway, we've accomplished some really cool things this semester, and one of them was building this little circuit right here, the DPScope SE. Now, this was designed by an Austrian gentleman by the name of Wolfgang, and not only did he design a really cool circuit, but he documented the heck out of it. And he did an amazing job of documenting that. So, and he's been super helpful at getting this into our hands, and is excited to see it being used for education, which is kind of what he meant for it to. Why he meant for it to exist. And so we're really happy to be using this. And one of the things is when I got you to build this circuit, I didn't talk about how it worked or anything about what it did, because at that time it was just going to be and make no sense whatsoever. I just said, read Wolfgang's instructions, put it together, and we'll talk about it later. Well, this is the last week of the course, and so this is later. And here we go. Let's take a look at the board. Now, I know you've got your board packed up in a nice little case, so I opened mine up and I took a couple pictures here, and this should look fairly familiar to you. From all of your soldering, you're going to remember taking a look at the back of the board over here. Now, on the back of the board, you can see that just about everything on the back is just like one solid piece of copper all the way around here. That's pretty typical on multi-sided boards, and that's what we call the ground plane. So it makes it easy when you're routing the board, because so many connections go back to ground that you need to have an easy way to connect things to ground. So you'll see that a lot of your solder joints come through here, and they just connect straight to ground. Okay, and there's a very, very few signals where you couldn't route them on the top of the board because they'd interact with other traces the wrong way. And you can see right along here, this line runs back to here, and this line kind of comes over here. And those are deviations from the ground plane where he actually uses the second side of the board, the back side of the board, for transporting a signal. But by and large, everything on here is grounded. One of the reasons that works really well in a circuit, and you see it done a lot, is because not only do a lot of signals go back to ground, but because ground is so common throughout your entire circuit, you want it to be at 0 volts. So if you've got a lot of copper in there, you don't get very much voltage deviation across your circuit. The other thing it can do is it can help reduce electromagnetic interference. So certainly we're not really worried about that at the frequencies and power levels that we're working with the DPScope and our high school electronics projects. But certainly when you're building commercial electronics and you have to get through industrial and national testing standards, having ground planes and having your circuit board designed to reduce electromagnetic emissions is a really, really good idea. So anyway, looking at the back of the board, you're going to see a ground plane and not a whole lot of other things. That's why I've got it in a small picture, just right over here. And right beneath me down here, I've got the schematic laid out. And again, the schematic looks like it's got a lot going on there, but we're going to walk our way through it, and I will zoom in on that so you can see it more closely and follow along as we go. And we're going to talk about what this circuit does and how it does it. Well, you already know what it does. It's an oscilloscope. It reads data, and it shows it on your screen. And it's a pretty cool circuit too. A lot of magic going on in the software, but today we're just going to take a look at the hardware. Okay, so the reference I'm using for this, and I don't want to pretend that I'm making this all up by scratch. I'm actually going through something that Wolfgang wrote. So if you would rather, just go ahead, Google DPScope SE, and it'll take you to the Instructables page or to dpscope.freevar.com, I think is the website. But anyways, take a look at that, Google DPScope SE, and it will take you to Wolfgang's original documentations. And he says it better than I do because he's the circuit designer. And we're going to walk through where he talks about some of the things that he does on his circuit. So if you want to open up those files, just put me on pause right now, And this is on Instructables right here, but you'll find the PDF version of it on Wolfgang's website. And you can play the home game as we go along. You can even break out your DPScope and take a look at it and say, oh, that's what that's doing in there. Because I think most of it's going to make sense to you because it uses concepts that we've used elsewhere in our course. Okay, so just a few things about the overall board that are going on right in here. So we've got two chips right here. And the big chip down at the back is a PIC microcontroller. The PIC microcontroller, very similar to that Mega 328 microcontroller on your Arduino Uno. So if you know how to use an Arduino, you understand the basics of operating a PIC. In fact, before I switched over to using Arduinos, and I only switched because of the massive amount of open source software available, I used PICs quite a bit. There's a nice little free graphical basic compiler called Great Cow Graphical Basic that you can get for the PIC microcontroller. You drop your code onto it. Works great. Love the PIC microcontroller. This one's a little more powerful and faster in some ways than what you're using on your Arduino. Okay, and that's why it's here and that's why it's useful. And one of the nice things about this particular chip is it's got the USB interface all built into it. So there's just a couple of traces coming off right here that then come in and connect into your USB port right here. Now the whole function of the microcontroller is to do the equivalent, if you're familiar with Arduinos, analog read. It's going to do an analog read, it's going to get a number, and it's going to get a number for each of our signals that are coming in, and it's going to punch that number right down the USB line back to a piece of software that's running on your computer that's going to display the graphical display. There's a bit more going on than just that, but that's the basics. Okay, so that's what this chip is doing right here. And it runs on 0 to 5 volts, which is good because our USB input gives us 0 to 5 volts. And right here, we have a quad op-amp chip. Now, in one of our circuits, we use the TL082. That's a dual op-amp chip. And you're going to see some of the same circuits and concepts being used here that we used in our Earrie circuit, which is in a previous video. I've also got an instructional video on the site here talking about what op amps are and how they work. So if you're not quite clear on the op amps, go back and take a look at that again, or Google it. There's lots of information out there on what op amps are and how they work, and there's no guarantee that my explanation is going to be the best. So basically what we're looking at right here is the signal is going to come in over here, and then we're going to do some signal conditioning right in this section. This is for channel 1. It's going to come into the op amp where it's going to get strengthened so that we can deliver a good signal to the microcontroller, which is going to digitize it, and then it's going to send that signal out the USB onto your computer where it'll be displayed. So let's get going in here and take a look at how things come together. There's picture of the screen, picture of it in the case. You'll notice that in Wolfgang's diagram right here, he's using a BNC connectors. In our case, we used RCA connectors. The BNC connectors are for a more traditional oscilloscope probe, and you've used them on some of the more traditional oscilloscopes that we have in the shop. All right, so he talks a little bit about his motivation for making the circuit and some of the things that existed at the time when he was designing this and ways that he wanted to do things a little bit better. And he's accomplished all of these goals in a really neat way and packaged something up that's great for educational at-home use. I figure it cost about $30 by the time we packaged together the entire kit, and so that was a nice thing to do. And he was avoiding the fine pitch surface mount soldering parts. And anyway, so he talks about some of that, and then he gets into the circuit overview. Now I've got the schematic on the screen right in here, and we'll be able to take a look at that. So I'm not going to leave this one up over here. I'm just going to scroll past it a little bit, and he explains what's going on right here. The signals to be displayed enter on the left-hand side. Okay, so let's take a look at that. And I'm just going to zoom in on this part of my schematic right here. And this is where the signals are coming into the board right now. Now, this is the equivalent of this part of the physical circuit. And you can see that we have an RCA connector in ours. So this is where he's drawn in the RCA connector, is right over here. Okay. And on our circuit, we've got an RCA connector. Well, I don't have red. Let's just pick out a color right there. There's our RCA connector right in there. And you can see that his center pin right in here is going to be the positive signal, and the ring around it right down here is going down to ground. So if you look on your board, what you can see is that the outer case, the shell, is all linked into these large terminals right here. They go straight through the board, and they end up coming out on, let me just flip screens around here. They end up coming out right back over here on the back of the board and into that ground plane. Okay, now he's got some other stuff drawn in here. And so right down here, he's drawn in a BNC connector and a jumper right over here. These are two alternate ways that he's provided for you to get the signals into the board. So for instance, if you were using the BNC connector, your signal would have come in right in here. Okay. And if you were using just a plain little jumper, you could put a header strip in right there and plug some wires in, and they would have come in right in over here. Now, all of those signals that are coming in, those different places, are going to meet up. And in this diagram, they all come along this one common line right here. And the first thing that happens to them is they come to a resistor and they come to a capacitor. Now, I do want to point out that his capacitors, he's using the polarized signal that we interpret as an electrolytic capacitor, and it looks like it's the wrong way around. I'm guessing that was the schematic symbol that came up on his software. And we draw it with two flat lines, but as you'll see when you take a look on the actual board, he's ended up using non-polarized capacitors right here. Because let's take a look in here, and I'm going to choose maybe a color that stands out a bit more against the red. And so here's our signal. It comes in right here. We've already talked about where the ground goes. And it follows this line right down there. There's where it can come in from this jumper right there. There's where it comes in from the BNC connector if you use one. And here's where it comes back to a resistor. And there's where it comes back to a capacitor. So you can see C12 is right in there and R1 is right in there. Okay, so that's where our signal's coming in. Now, just before I talk about what's going to happen on the other side of that, I want to jump to a different part of the circuit that I hope makes a lot of sense to you, and that's going to be right down over here. Because right down over here, we have a positive and a ground and some resistors in the middle, giving us a voltage divider. Okay, now we used a similar concept to this when we were setting up our op-amp, the TL082 op-amp. As you recall, we created a fake ground level. Okay, we called it a 4.5 volt reference because our power supply for the TL082 was between 0 and 9 volts. Yet we wanted the speaker that we were using on there to be able to move back and forth, and we knew that the sound waves that were hitting our microphone on the Earrie were going to try to make it move back and forth. So by creating that fake ground level, we could have voltages above the fake ground and voltages below the fake ground. So right here, Wolfgang's doing the exact same thing that we did on that circuit. And he's gone and done a little trick. He's made it adjustable. Okay, which is really cool because you'll notice that these resistors right in here are only accurate to plus or minus 5%. So he didn't know exactly what voltage level was going to come out in here. So when you were calibrating your DPScope, you'll recall that the last thing you had to do after you got it assembled was come in here and take this potentiometer right here, and this one for channel 2, and you'd take that potentiometer with a little screwdriver, you'd put it in there, and you'd turn it back and forth until your zero voltage level was sitting right where a zero voltage level should be on your software. Well, that's because you were tweaking this up and down until it was reading exactly halfway between plus 5 volts and ground. So you were getting exactly 2.5 volts coming out right in there. And so this signal coming out right in here is a 2.5 volt reference. Okay, this capacitor right here is just here to keep that from bumping up and down too much on us, okay, because signals are coming in here, they're going to be changing things, and this little capacitor just keeps everything nice and steady at 2.5 volts. Now, this looks a little different from the some of the voltage dividers we use because there's a potentiometer in the middle of it, but keep in mind that as you spin that dial back and forth on the potentiometer, what you're doing is you're breaking one big resistor into two small resistors. So right up here, you've got a combination of R16 plus the first half of the potentiometer R12. And then down here, on the other side of the voltage divider, you've got R17 and the second half of R12, that variable resistor. So what that's doing is you get that set once, you leave it alone, and then you've got 220 ohms up here, plus a little bit of R12. And on this side, you've got 270 ohms down here, plus a little bit of R12. And that gives you your 2.5 volt reference out right here. Now, when you take a look at where Wolfgang starts describing this and analyzing all this, let's see, here we go. On the input stage, his explanation is excellent, and it's kind of what I've got this based on, actually. So like I said, go ahead and read it because he's done a good job of writing this up here. You'll see him refer to this chunk as the low impedance divider, and this is the high impedance divider. Now keep in mind, impedance is just another $5 word for resistance. Carries a few more meanings because impedance is also used to describe what happens when you run alternating signals, which we're looking at here, through capacitors and inductors. And you can get different, slightly different meanings on impedance and resistance, but until you get into AC signals, which we really haven't dug deeply into yet, you can say impedance, resistance, roughly the same thing. And certainly in this circuit, it works out to be close enough to the same thing that we're okay using that. Okay, so now what we've got is this part of the circuit right in here. Let me flash back to our schematic right here, is going to be sitting at 2.5 volts right in there. Okay, I should really be doing this with a touch screen. It would probably come out neater. And right here, we've got another voltage divider. I told you we're going to have a lot of voltage dividers in this course. Here comes another one. And this side's got 909 k ohms on this side, 100 on this side. So about a 9-to-1 ratio on there. So what that means is that the voltage that's coming in here is roughly 1/10 of the voltage at this point than it is out here, because you've got a whole range of 10 right on there. Okay, so in here, another voltage divider, and it splits this voltage down to 1/10 of whatever it sees on the input comes out right there. But that is also, okay, 1/10 of the difference between the input voltage and 2.5 volts right there. So what you end up with is, if you're reading a negative signal relative to ground on your input, instead of it going all the way down below 0, which we wouldn't be able to read on our microcontroller, it goes down below 2.5 volts, which we can read on our microcontroller because it's still above 0. You understand that? No? press pause, read what Wolfgang says, think about it a little bit. Take a look at the Earrie circuit where we used a 4.5 volt reference so we could have voltages above and below. And he refers to this as our high impedance input. So basically what that means is by having a lot of resistance here, it's not going to mess up our reference voltage right here because there's not very much current flowing this way. Okay, so now that is going to go into our op amp, but there's a few other little things going on. Now, just before I go on, this using a voltage divider to drop a voltage by a factor of 10 is one of the very first things we did in the course. Remember when we were using our Arduino as a voltmeter? And we said, well, it works really great at measuring voltages from 0 to 5 volts. Yay. But what about 0 to 20? And we dropped a voltage divider in there to split the incoming voltage, so we only saw a quarter of the incoming voltage, so our 0 to 20 range dropped down to a 0 to 5 range. Well, here what we're looking at is Wolfgang's done the exact same thing, but with a 10 to 1 ratio. He's actually giving us a 50 volt range from positive 25 down to minus 25 volts relative to ground on this circuit, which was actually one of the questions I asked. Didn't get an answer on it back at the time when we were talking about the Arduino voltmeter circuit, was how could you measure a negative voltage? Well, here's the answer. You do what Wolfgang does. You provide a fake reference rather than ground in order to compare your incoming voltage to. All right, now he's got a couple of capacitors in here, and we didn't really talk a lot about capacitance dividers. Okay, now in his text, follow this along, and he talks about this right in here. The microcontroller's analog to digital has a fixed input range of 0 to 5 volts. Okay, and input stage is attenuated by a factor of 10. So this is all coming in right here. He makes a few references to standard scope probes. We're not using it with standard scope probes, so that's okay. But you can hook this up and you can plug in, if you use the BNC connector, a standard scope probe, and that's why he chose the 100 kilo ohm resistor and the 900 kilo ohm resistor. Is by putting them together you get 1 megohm, which is the input impedance or the input resistance that those scope probes are expecting. Okay, he talks about the fact that the remaining circuits can't handle negative voltage and adjusting R12. Okay, and he talks about the offset voltage right in here. So you can follow along in his document and see all of the things that we're talking about right here. And so if you'd rather not watch the video, go ahead and watch that and or read that, and then everything I'm saying will make a lot more sense if you read what he said. Okay, now he refers to the input divider as an attenuator. Remember, we talked about amplifiers that increase signal strength and attenuators that decrease signal strength. So that's just the big word for saying we've got a voltage divider in there. It's weakening that signal strength. It's taking it from minus 25 to plus 25 and dropping it down into a range that runs 0 to 5 so that our op amp can handle it and our microcontroller can handle it. Now, the capacitive divider has some magic electronic juju that we haven't really talked about, and in most of our circuits we tend to ignore, but we did talk about resistor, capacitor, time constants, and RC filters when we were using the I'm forgetting all our circuits now. The Color Organ Triple Deluxe. We made that, and it works extensively with RC filters to break an audio signal into high frequency, low frequency, and mid-range frequencies. So what he's saying right in here is that there is this thing called parasitic capacitance. And you know how we don't always mention things like when we first did electronics, we didn't talk about the fact that, you know, the copper lines on the board had resistance or that wires had resistance. That starts to become more important as you go along. Well, so far we haven't talked about that all these things have a little bit of capacitance too, because we've been able to ignore it up until now. In this circuit, there is a tiny little bit of capacitance on these diodes, and we'll talk about the diodes in just a minute and why they're there. And there's a tiny little bit of capacitance on this input pin, and you probably get a little bit of capacitance and even a little bit of impedance along this signal line that's running right through here. Well, anyway, if you have that tiny little bit right there, because your resistor is so big right up here, okay, the current coming through here is absolutely tiny. Okay, 900,000 ohms. There is very, very little current coming through right here. And if you've got a tiny little bit of capacitance right in here, it's going to take a while to charge that and discharge that. So any of your higher frequency signals are just going to get absorbed. You've got an RC filter. Although the capacitance of your filter is very, very tiny, the resistance is very, very large. And you'll recall that the time constant is based on the resistor times the capacitor. So because the resistor is giant and the capacitance is small, you're still going to have a value in there. So what he does is he puts a capacitor right in here and right here down to ground. Now, what that allows to happen is these high frequency signals that would get absorbed in this network right in here, okay, and right down here, that would get absorbed by the parasitic capacitance. The high frequency signals get to bypass right around R1. They come right in here, they sneak in here, and they go right through here and they get read right away. They don't get attenuated as much. And you'll recall that on our Monobox, our amplifier, we used a capacitor in a similar way. We let the high frequencies come through on our amplifier circuit because they came back on the feedback and wiped out some of the high frequencies from being amplified. So the net effect was that we got a bass boost coming out of there because the bass was being amplified more than the high frequencies. So our little speaker sounded a little bit like a bigger speaker. So little tricks like this that you've used on your previous circuits tend to show up a lot of times. And the thing is, you might not fully grasp what they're doing right now because you've only seen them once or twice. Okay, you're not expected to fully understand everything the second time you see it. But the things you did on the DPScope, which is a fairly sophisticated little circuit, are the exact same things you're doing on your breadboard with your little capacitors and resistors, plugging them in there on all these basic circuits that you might do with a high school student. And that's going to be setting your high school students up if they go on to become an electronics technician or an electrical engineer. They're going to have seen some of these things before. And if you can give them that little bit of an edge so they understand it and they approach it with a little bit of confidence when they get on to the post-secondary level, you're doing them a big favor. And they might not feel it at the time that you're driving it into their heads, but it pays off in the long run. And we don't even really know that. And I know you guys have seen similar things where you come into the program with a skill that you learned years ago, and it feels good to be able to show people how to weld or how to use the wood lathe or stuff like that. So this is giving your future students, just that little bit of, oh yeah, it's just a capacitor. High frequency signals pass through it easy. See? It's a really small capacitor. It's only 24 picofarads. You'd have to be a really high frequency signal to get through there. And if that made sense to you, you're doing good. And if it made a little bit of sense, well, you're still doing okay. Alrighty, so our signal comes through right in here. Low frequency signals will blast right through here, no problem. High frequency signals take this little bypass and come right down here. Now, where this all shows up on our circuit, well, here is that C12 right up here, where those high frequency signals pass through. There's R1, so those signals pass through right here. They come in, they meet up at R3 and C11 right here. The other side of that just goes straight down into ground. You can see that actually, I guess that's right down here because it's kind of a mirrored image. That's going right into that big ground plane. Okay, so those come together right into there. And we've also used, here's those resistors right in here that we've used to set the reference voltage right here. So if you take a look on the opposite side of this right in here, there's a little, where does that little line come off right in there? Oh, it's snuck in here on the back right there. There's our reference line coming right through on the back. So you can see your potentiometer sits right in here, and that signal on the back just comes right through in here and jumps up into the circuit over here, and that's what's setting our low voltage reference right in here. Okay, so our circuit comes in here, the high frequency stuff gets to bypass so that we get a slightly stronger high frequency signal, and he admits in the text that, yeah, that's not an absolute perfectly great thing, but it's good enough for the purposes of this circuit. Then it flows on, it comes right through here, okay, comes back this way, and we come to these two diodes. Okay, now these diodes are protection diodes, and we use protection diodes in our power supply. Now, the whole point of the protection diode is if the voltage at this point in the circuit right here ever exceeds 5 volts, then electricity can flow right up that way and it gets absorbed. And if it ever drops below 0 volts, then electricity will flow in here from ground, and our power supply will take all of the hit. It will absorb that high or low frequency level instead of it coming into our op amp or into our microcontroller and damaging one of the chips. So this is here to protect our chips. Now, when you read his text, he points out that, yeah, that there are protective diodes built into the chips, which is pretty common. But because we have no idea who's going to be plugging this in or where it's going to be going, he adds some extra protective diodes. And I have to admit, you've seen this in at least one of my videos. When we were looking at the power supply, my DPScope stopped working because I was using it to read an AC signal that every now and then, at its peak, would peak up above 25 volts. Its RMS signal was well below 25 volts, but you've got to remember that the peak of an AC signal is quite a bit higher than its RMS voltage. Alrighty, so protection diodes right there. Really nice thing to have in your circuit. And now this conditioned signal comes in here over to our op amp. And so you can see he talks in here, he's got a ratio for how to set up the your capacitor divider. And in his text, he gives you the formula right here. So if you wanted to be able to use this circuit to measure higher voltages, you could adjust the resistors in the voltage divider. Just make sure you adjust the capacitors in the capacitive divider. And so you could change this so if it's absolutely necessary for you to use the DPScope to measure from 0 to 50 volts, or minus 50 to plus 50 volts, you could change that around and you could make it work. Okay, let's see, the two diodes, he talks about the input protection. Now there's the amplifier stage right in here. Well, when we built this circuit, there was no point talking about the amplifier stage because we hadn't looked at amplifiers yet. But your signal is going to be coming right in here on pin 10. And let's take a look. There it is on pin 10 right here, and it's an op amp. And the op amp will have its +5 on the top and ground on the bottom. Now you'll notice in the text that he refers to this as a rail-to-rail op amp. This is different from the TL082 that we used. It's not a rail-to-rail op amp. In fact, it's got some headroom at the top and some headroom at the bottom. So even when we hook it up to a 0 to 9 volt power supply, you can't go all the way from 0 up to 9 because the chip is using some space at the top and the bottom, and it needs some of that overhead to work. This is a little more sophisticated chip, and if you give it a 5 volt power supply, it can sense right down to 0, and it can sense right up to 5, and it can amplify right down to 0, and it can amplify right up to 5. Okay, so it's got +5 up here, ground down here, positive signal comes in right here. And here is our feedback loop right in here. And you'll recall when we take a look at our op amps, when the signal comes back like this is what we call a unity gain op amp. In other words, the gain factor is 1. You put 1 volt in there, you get 1 volt out of it. And this is what we did on the Earrie circuit with the TL082 to get our 4.5 volt reference. We give it a weak signal at 4.5 volts in the case of the Earrie, whatever our input is right here. Okay, so by weak signal, I mean it's got the voltage, but there's no current behind it to speak of. Okay, and what he does right in here is this op amp takes it, the feedback comes back in here. So if I've got 1 volt coming in on the positive, it's only going to be happy. The op amp's only going to be happy when it sees 1 volt on the negative. And so this signal is going to come right back around here, feedback in here, and our output has to be at 1 volt as well in order for this op amp to be happy and stop amplifying. So there we go. Unity gain op amp gives it enough signal strength so that it can blast through right on here and come in pin 15, which you'll see on the PIC chip is marked as analog pin 5. Okay, and we can track that coming down right in here. Here's our PIC chip. 1, 2, 3, 4, 5. How many pins have we got here? There's 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Now there's 15. I don't see anything coming out of that on the top. But if we come around and look at that on the bottom, I can see a line that comes right out in here. And we want to pick that signal up where it comes in off of the op amp. So I'm falling behind down here. Where does it come into the op amp? It comes into the op amp on pin 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We don't see anything on the top right there. Aha, right there. There's pin 10 on the op amp. And let's just mark that up. So that signal actually jumps over to the back, comes off those 2 protection diodes right up here, okay, and then sneaks around to the back. There's our +5, and this one just goes straight down to ground. And let me just take a look at that right on there. Oh yeah, that's part of the connection on the back to that other diode. Nice routing. It's a nicely designed board. So that comes into the op amp right there. The output from the op amp comes out on pin 8. So let's see. I've got to convert my head around. I guess this is pin 1, 2, 3. Sorry, pin 1 right there. You can see the little square right on that. Okay, if you look really closely, he's got pin 1 marked on the back. I've got to remember it's flipped over like that, so it's a bit of a mirror image. 1, 2, 3, 4, 5, 6, 7, 8's right here, so that's our output right there. It's going to be soldered into pin 9 right there. There'll be a little connection on one side of the board or the other, and then it's going to come right off of there. And where does that signal go? Right up here, there's pin 8. Comes right out here, and you can trace it along back here, and it comes into pin 15. And that's where it's going to get digitized. So that's pretty much the input stage. Now there's a few other interesting things going on down here, and some of them we haven't really used with our use of the DPScope yet. But hey, now you get to find out about them, and you get to take a look and say, well, what's going on right in here? Well, here we've got our signal. After it gets amplified, you know, part of it comes back in here, but part of it comes down to a second op amp. So this voltage here on pin 12 is at the same voltage as at pin 10. It's just been amplified a little bit. Now, he's used a good quality op amp on here. Op amps come in a whole range of characteristics and performance abilities, and this is a fairly fast responding one. You don't want to use the cheapest op amp you can because we're looking at 300 kilohertz signals, which is pretty trivial for an op amp to amplify cleanly. But if you were building a more advanced scope, that was going to take a look at megahertz signals, then you're going to need more advanced amplifiers that can accurately amplify the more advanced signals. We're keeping it down to 300 kilohertz, which is pretty much everything you need for high school electronics. So we can get away with slightly less fancy op amps. And basically what's coming down here is it's coming into a second op amp right here, but you'll notice that their feedback loop right down in here, R7, okay, comes down around this way, and it comes to another one of these 2.5 volt references right in here, okay. And so what's happening right in here is that we've got basically a 10-to-1 voltage divider in here again, which gives us a 10-to-1 gain on this op amp. So whatever signal we get coming out here is just whatever signal we put in right here. But if you're looking at a finer signal, okay, maybe like the input to your Earrie, well, you could read it off this pin and bring it in right here because this one is going to be 10 times higher than the voltage right here. Now, it's still going to clip, right? It can't go below 0, it can't go above 5, so it's not like you're going to damage your microcontroller by sending it the signal from right here because the op amp can only go down to 0 and up to 5 voltages that the microcontroller can handle no problem. But it comes right back into there, and you can go ahead and you can read those signals. And when you're running the software, you'll see a little tick box that has a 10-to-1 marker on it. And you'll have to go back and take a look at the software again. And if you see that 10-to-1, what you're actually doing is you're switching your inputs, okay, and you're reading from the 10-fold amplified signal. So that if you're bringing in 0.001 volts, which would result in a very tiny reading in here and not very accurate if you read it on pin 15, you'll amplify it tenfold and you'll get 0.01 volts, okay, which is going to give you a lot more accurate reading on pin 14. And you just hit that one little 10-to-1 button on his software and it switches the input over for you, and it should change the scaling on the inputs, and away you go. And that is most of the magic that that's the most of the magic that the hardware is doing on the DPScope. Now there's a lot more to the schematic than that. If we look down at this side right here, you'll see that this is channel 2, and it's basically just a mirror of what we did on channel 1, because all the processing is pretty much the same. Now, there's a few interesting things going on in the middle right here. This is our USB connection right in here. Okay, so basically just a few little things about signal processing on a USB that he talks about, using a coil to keep your 5-volt line free of coil and a capacitor, an inductor and a capacitor, keeps the 5-volt line free of noise on the power line because that could interfere with your circuit. Right in here, he's got a circuit that senses a trigger level. Okay, now this is an automatic trigger level, so you can adjust the trigger level right here. Feeds it back into something called a capture compare register or a comparator inside the chip, and that's getting into more of the software side. I want to just talk about the hardware side today. Let's see, what else does he talk about right in here? So we talked about the amplifier stage, a little bit of the things that he did on the amp. Here he's got his ratio laid out for the gain that he calculated for the op amp. And then he goes in and he talks a little bit about the trigger and how it works. It uses a comparator. Okay, now the comparator is built into the microcontroller, but you'll also recall we talked about comparators when we were talking about op amps. Pardon me. Maybe I should have hit mute there. So he's got a comparator built into the microcontroller, and basically it's the same as using an op amp as a comparator. It just happens to be built into the microcontroller. And in fact, your Arduino has that set in there as well. Now, a feature about the DPScope that we haven't really talked about is your logic analyzer, and that's this pin out right down here. The 5-volt pin isn't connected and implemented yet because he's left room for a little fuse right in here. You can put a self-resetting poly fuse right in here. The idea being that you'd be able to plug an external circuit into this, power the external circuit off here, and rather than read analog signals like we do on an oscilloscope, a logic analyzer reads digital signals. That makes it a lot simpler to read, so you can have more channels coming in right here and you can actually read that data faster. So if you're trying to analyze something that's going on on a digital circuit, you can use these pins right here and you can actually look at 4 different signals. So say you were trying to figure out what the LCD screen on your big bad breadboard board was trying to do, you could hook up onto these 4 little pins at the end. I like to keep some jumper wires like this handy nearby and just hook one into ground. And how many have I got on here? Anyway, I assume you're capable of hooking up the rest of the plugs, and I put them in like that, and then I can plug that into a circuit board and I switch it over to logic analyzer mode, and you can go ahead and you can look at 4 channels of digital data and record that and say, oh, how is that signal changing over time? Which bits are being sent first? And we haven't got to that level yet where you've had to do that, but you should know that that's available for you as an option. So we have yet to maximize everything that this DPScope can do. Those channels come back right through there, through those resistors, just so that in case you get a high voltage signal, it doesn't end up toasting your microcontroller. Let's see, anything else we need to do? He talks about his USB connection down there. You can see the USB right there. The capacitors that are tied into it are right in there. There's that little ferrite bead or coil that is marked off as L2 that comes in right in here and runs right through there. So like he says, the whole USB interface is already built in. He spends a little bit of time talking about the mechanical design, which I think is really rather brilliant, using a pre-manufactured case, but having the front panels made up at the printed circuit board factory where they do all the fancy cutting and all the fancy marking, so that when you get it, you just put everything together and it fits. Really, really nice design. So then he gets into the instructions, and he sold this as a kit for many years, and we was kind enough to actually haul all of his equipment out of storage to burn some chips for us so that we could make these. And I look forward to making this project with my students for a few years because I think it's going to be really useful. And I hope you're sitting, taking a look at it, and saying, "Oh, op amps. Reading an analog input with a microcontroller. Voltage dividers. Actually, a lot of voltage dividers. Resistor capacitor circuits and filters." These are some of the fundamental concepts that you're going to build on during the rest of your time taking a look at electronics. And you can go a long way with some of that fundamental knowledge and keep building upon it, block upon block upon block. And yeah, I know we've rushed through it. We're trying to cover, if we wanted to give you 100% of an understanding of what you need to be an electrical engineer, well, that takes 4 years and a full-time study. We're trying to give you a little bit of an introduction to some of the terms and concepts that you'll see. So if you're teaching electronics in the high school, you'll be able to start relating them to things that you've seen before and tying them together. And over time, life will start to get a little bit easier. So that's my annotated view of the DPScope. It's really, really brilliant circuit that uses really fundamental things that you've already done in the other circuits you've made in TTED 4060. I think it's time for a drink.